Alright, welcome back, generals, to another Let's Fix Generals Zero Out to make the best game ever, and we continue looking at this MachO file format reference to get an understanding of what this gives us. So, last session we have seen how it describes the segments and, the sections inside the segments. And what else do we have here? Let's see. Let's see. Each section in a MachO file is both a type and a set of attribute flags. In intermediate object files, the type and attributes determine how the static linker copies the sections into the final product. Object file analysis tools such as OTools use the type and attributes to determine how to read and display the sections. The section type and attributes are not used by the dynamic linker. These are important variants of the symbol type and attributes as they apply to static linking. Regular sections. In a regular section, only one definition of an external symbol may exist. One definition of an external may exist in intermediate object file. The static linker returns an error if it finds any duplicate external symbol definitions. Makes sense. Coalesced sections. In the final product, the static linker retains only one instance of each symbol defined in coalesced sections. Some complex language features, such as C++ vtables and RTTI, which we are very much interested in, waste a lot of space in the final product. But it's good if it's there, right, for us. To reduce the memory occupied by a program, the compiler can place symbol definitions in coalesced sections. Coalesced sections with weak definitions. Weak symbols definitions may appear only in coalesced sections. When the static linker finds duplicate definitions for a symbol, it discards any coalesced symbols definitions that has a weak definition attribute set. See analyst page 69. That's an upcoming page. If there are no non-weak definitions, the first weak definition is used instead. This feature is designed to support C++ templates. It allows explicit template instantiations to override implicit ones. Explicit template instantiations. It allows explicit. So I think this refers to template specialization. I think, yeah. Template instantiation to override implicit ones. I think so, yeah. C++ compiler places explicit definitions in a regular section, and it places implicit definitions in a coalesced section marked as weak definitions. Intermediate object files. And those static archive libraries built with weak definitions can be used only with a static linker. Final products, applications, and shared libraries should not contain weak definitions, so they usually can be used on earlier versions. The data structures of okay, two lines command. Okay, we don't care, I think. Yeah, whatever. The static linker adds blah blah blah. I think we don't care about this. Yeah, okay. Do we care? No, I don't think so. LCSTR defines a variable length string. Okay, LCSTR. It's either an offset or a pointer. Okay. A long integer. A long integer. A byte offset from the start of the load command that contains the string to the start of the string data. Pointer to an array of bytes. At runtime, this pointer contains the virtual memory address of the string data. Okay. Load commands store variable length data, such as library names, using the LCSTR data structure. Unless otherwise specified, the data consists of a C string. The data pointed to is stored just after the load command, and the size is added to the size of the load command. Okay. You can determine the size of the string by subtracting the size of the load command data structure from the CMD size field. Okay, I see. Defines the data. Yeah, I don't think we care about this guy. Dilib. Timestamp conversion. So I think it's this one here, right? Weak dial-up is done. Lazy loads. Current version, compatibility version. Yeah, it's this one here. I see. Convert here, timestamp. Yeah, okay. So leaf also has information for this guy. So we don't care about this. Okay, what else do we have here? Dial linker command. Pre-bound dial-up command. The data structure is a load command for every library that a pre-bound executable file links to. A pre-bound executable file for every library that a pre-bound executable library file links to. Pre-bound dial-up. Okay, so it's like a it's a required library. I don't understand. So this is dynamically linked. And what about this one? Do we care about this pre-bound? Data structure. Okay, I don't understand what this is supposed to be. Thread command. The data structure for the LC threads. Data of this command is specific to each CPU architecture and appears in thread status. So is there like is there something in here? Binary. Does this contain anything about threads? Doesn't look like it. No. Let's search for threads. Thread command. There is something. Okay, where's this contained? Or what does this contain? Flavor, architecture, state, PC. Architecture. Flavor, yeah, okay. State. Okay, so it's all also already covered. Routines. Routines. Okay, we don't have a match here on routines. Data encode. What is data encode? LC data encode commands. The slices. Dynamic symbol commands. Well, they did some documentation here, and then they just stopped. Too much here. Let's stop the documentation. Okay, well, there seems to be no routines. Data structure LC load command describe the location of the shared library initialization function, which is a function that the dynamically. Okay, we don't care about that. We don't care. Sub-framework command. Don't care. Umbrella. No care. No care. Name of a file that is allowed to link to this. Okay, we don't care. Symbol table. Okay, now it gets more interesting. So symtab is certainly something we're interested in. Describes the size and location of the symbol. Symtab command. So this refers to this one here. It has symbol offset. Let's see, down here. Symbol offset, symbol string offset, str size, NB symbols. Yeah. Symtab should exist in both statically linked and dynamically linked file types. Nlist describes an entry in the symbol table. An entry in the symbol table. It's declared an nlist. Okay. A union that holds an index into the string table. Okay, what do we have here? A byte value and type. And type. So, and type probably refers to this guy here, right? And step E0. If any of these 3 bits are set, the symbol is a symbolic debugging table entry. A symbolic debugging table entry. Okay, so STAB stands for symbol table or something like that. Yeah. In that case, the entire n-type field is interpreted as a step value. See step.h for valid step values. Okay. Okay, we should look at that then. Let's copy this section here. Okay. npExt 10. If this bit is on, this symbol is marked as having a limited global scope. Limited global scope. What is it? What is limited global scope? When the file is fed to the static linker, it clears the next bit for each symbol with a npExt bit set. Keep private externs turns off this behavior. Private extern. Private extern. A limited global scope. Private extern. Okay. I wonder if this is ever the case in our MachO binary. Maybe it's never the case because private extern, this doesn't exist. I think this doesn't exist in Visual Studio compiler. Microsoft Visual Studio compiler. So I don't know. A limited global scope. So so if this is set, it is a private extern type. N type 0E. These bits define the type of the symbol. These bits define the type of the symbol. Okay. And then there's bit 1. If this bit is on, this symbol is an external symbol. Okay. An external symbol. A symbol that is either defined outside this file or that is defined in this file but can be referenced by other files. A symbol that is either defined outside this file or that is defined in the file but can be referenced. Okay, so it's basically you have a header file and you type extern int variable name. That would be this extern. So something that has an extern keywords. Okay, that's interesting. Okay, I can work with that. Values for the end type. So this is actually useful information. This is something we need to work with. Yeah. And we need to look at then the step.h file. This seems to be relevant. Values for the end type field include. What is end type? This here. This one. Zero undefined. The symbol is undefined. Undefined symbols are symbols referenced in this module, but defined in a different module. Undefined symbols are symbols referenced in this module, but defined in a different module. Nsect. Set the nsect field to no sect. What is nsect? Nsect. Oh, what is nsect? I don't know. Nsect is this one here, but what does it refer to in leaf? Section, number of sections. Let's search for section here. Sect. Section. Type. Pre-bound. Type. I'm confused. Number of sections. Returns the number of sections in which the symbol can be found. If the symbol can't be found in any section, it returns 0, no sec. Number of sections. Nsect. Nsect. In the section number given in nsect. I'm confused. But this one says number of sections. Number of sections. So the number of sections. How does this refer to that? I don't understand. I'm confused. Because this one only talks about one section. The symbol is defined in the section number given, right? So it's one section number that and sect would give. No. I'm confused. That's weird. I don't understand like how this relates to the reference. Right, it's different. Number of sections, it's multiples. The way it's described here. It returns the number of sections in which the symbol can be found. If it would say it returns the number of the section, plural, singular, then it would match this here, but it doesn't. So I don't understand how this works. The symbol is undefined and the image is using a pre-bound value for the symbol. Set nsect field to no sect. EDR indirect. The symbol is defined to be the same as another symbol. The n value field is an index into the string table specifying the name of the other symbol. Same as another symbol. Okay. The n value field is an index into the string table. Okay. Specifying the name of other symbol. When that symbol is linked, both this and the other symbol point to the same defined type and value. Poof. Okay. This one is a bit complicated. I'm not fully... This needs a closer look. Integer and sect. So integer specifying the number of the section, so singular, that this symbol can be found in, or no sect 0 if the symbol is not to be found in any section of this image. The sections are contiguously numbered across segments starting from 1 according to the order they appear in the LC segment load command. The sections. I wonder if just the documentation here is incorrect. So this is a 1 byte unsigned integer. What about this one here? This one is... It's also unsigned 1 byte. So maybe this thing is that, but it's just incorrectly named here. Maybe the documentation is just wrong here. Yeah. 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 Likely. Okay. Okay, so we have some good information here. I appreciate this. So these category indirect an absolute undefined section pre-bound indirect. So this stuff here refers to this stuff here. Type to type. Yeah, okay, so this is a 0, this is a number 2. E, here we go. C, A. Okay, so this is exactly that. And this origin stuff, does this refer to anything here? Maybe not. Insect. Okay. Okay, what else do we have here? And desk. Aha, the description. We have seen this here. Here, description. But there's no documentation about it. Let's see. A 16-bit value. Is it 16-bit? Yeah. 16-bit value providing additional information about the nature of the symbol. The reference flags can be accessed using reference type mask and are defined as follows. Reference flag undefined non-lazy. Reference flag undefined lazy. Okay. Symbol is a reference to an external non-lazy data symbol. External lazy symbol is to a function call. The symbol is defined in this module. The symbol is defined in this module and is visible only to modules within the shared library. The symbol is defined in another module in this file. It's a non-lazy data symbol and is visible only to modules within this shared library. This symbol is defined in another module. Oh my gosh. Okay, I don't know how useful this stuff in the end really is for our purposes, but okay, we have some. There's more. Look at that. The following bits might also be set. Must be set for any symbol that might be referenced by another image. The strip tool uses this bit to avoid removing symbols that must exist. If the symbol has a bit set, strip does not strip it. And this discarded, used by the dynamic linker and at runtime, okay. And weak ref indicates that the symbol is a weak reference. If the dynamic linker cannot find the definition for the symbol, it sets the address of the symbol to 0. The static linker sets the symbol and given the appropriate weak linking flags. Okay. Okay. I don't know how useful this stuff is, but okay. We have a documentation. That's good. If this file is a 2-level namespace image, that is, if the MH2 level flag of the Mac header structure set, the high 8 bits of ndes specify the number of the library in which this symbol is defined. Use the macro get library ordinal to obtain this value and the macro set library ordinal to set it. 0 specify the current image, 1 through 254 specify the library number according to the order of lc load dylib commands. What if there are more than this number? What if there's a 255 or more? For plugins that load symbols from the executable programs they are linked against, 255 specifies the executable image. Flat namespace image, the high 8 bits must be 0. Okay, I'm not sure if this is relevant for us. N value, an integer that contains the value of the symbol. The format of this value is different for each type of symbol, as specified by the n type field. For the nsect symbol type, nsect that was nsect symbol type, this one. Yeah. For the nsect symbol type, n value is the address of the symbol. Okay. So it was a symbol linking to another symbol or something like this, right? The symbol is defined in the section number given in nsect. In the section number. And where is the address of the symbol? It's the address of the symbol and type. Okay. Discussion. Common symbols must be of type n undif and must have n x bit set. The n value for a common symbol is the size, n bytes, of the data of the symbol. And C, a common symbol is a variable that is declared but not initialized in this file. Common symbols can appear only in MH object. Common symbols must have nx bit set. And value for a common symbol is the size of the data of the symbol. And C, a common symbol is a variable that is declared but not initialized. Only an MH object. So this is not relevant for executable. Okay, data structure for DLC DISM tab, load command. I think this is not relevant for us. Set file offsets define the location of several other tables. If I'm not mistaken, the LC die sim tab count was 0, if I'm not mistaken, in our executable. All right. Table of contents, symbol index, okay, symbol index. So if you look at binary, Dialab module describes a module table entry for dynamic shared library. I don't think we care about that. Dialab reference, the structure of an external reference table entry. I do wonder if it... I don't know. Moving symbols to a different address. When a static linker moves a symbol, a functional item data to a different address, it needs to change all the reference to that symbol to use a new address. The relocation entries in a MachO file contain offsets in the file to addresses that need to be relocated when the contents of the file are relocated. The addresses are usually relative offsets stored in CPU instructions. The exact format of the address is specified in each relocation entry. When creating the intermediate object file, the compiler generates one relocation entry for every instruction that contains a relative address. Static linker typically removes the relocation entries. And building the final product as relocation local to a single MachO file does not usually occur at runtime. Removes building a final product. Relocation local to a single MachO file does not usually occur. I'm not sure what that means. And they really use the space efficiently here. Describes an item in the file. So what if you have more than 16 million symbols? That's the limit here. 16 million symbols. Well, that's a lot. But I assume that there will be projects that hit this limit. Big projects. Yeah. Our address. Yeah, I don't know if relocation is of interest for us. I don't think so. Class that represents a MachO relocation. I don't know. Probably not. Probably not. Where are we? Scattered relocation info describes an item in the file using a non-zero constant in its relocatable expression or two addresses in its relocatable expression that needs to be updated if the addresses that it uses are changed. What? This information is needed to reconstruct the address that make up the relocatable expression's value in order to change The addresses independently of each other. This data structure is declared in relog. I'm so confused. Well, my hope is that it's not relevant. Static archive libraries, ranlib. Section of file format used for static archive libraries, which are described in static archive libraries. See the discussion for the ranlib. What is this? Okay, I don't think we care about this. We only have an executable. Yeah. Multi-CPU architecture files. The standard development tools normally accept multiple CPU or FAT files as parameters wherever a normal MachO file or static archive library is accepted. The dynamic linker loads the correct data for the currently running CPU from FAT shared libraries, frameworks, and bundles. A FAT file is not really a MachO file at all. It is a simple archive format that contains the data of either multiple MachO files, one for each CPU architecture you wish to support, or multiple static archive libraries. Again, one for each CPU architecture you wish to support. You can have a FAT file containing data for only one CPU architecture, although it's not very useful to do so. Why not? A multiple architecture or FAT file is one that contains compiled code and data for more than one CPU architecture. A FAT file contains a set of single CPU files, one for each CPU architecture, with a special header at the beginning of the file to allow the various runtime tools to quickly find a particular CPU architecture. Each single CPU file is stored as a continuous set of bytes at an offset in the FAT file. The single CPU file may currently be either MachO files or static archive libraries. Single CPU files may currently be For example, a FAT static archive library might contain the data of one static archive library containing PowerPC modules, and also data for one static archive library containing x86 modules. I mean, yeah, for our case, it's PowerPC and x86, but I don't know if it's static archive library. Isn't it executable? I don't know. Maybe that wording is interchangeable. A FAT file always begins with a FAT header data structure followed by a set of FAT arc data structures. Okay, but we don't really care because Leaf already reads this correctly, so this seems to be fine. Okay. An array of FAT arc data structures appear directly out of FAT header data structure. File, blah 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 blah. Okay. Okay, that's it. Look at that. We are through. Well, we skipped a lot of sections. Basically, all the sections we weren't that interested about. Okay, so to me it looks like that we certainly want that we eventually get some we get some information about the symbol in relation to which section it is. This is something I wasn't aware about before, right? So it was up here somewhere. Let's try to find it. Oh boy. There was a table somewhere, no? Ugh. Here. Yeah, so I wasn't aware about this before, that, well, it's not the best table here. Wasn't there a better one? Yeah, this one here. So depending on the section the symbol will be contained, it tells us about something about the kind of the symbol, that maybe we don't get this information from anywhere else, right? So we eventually check the name of where the symbol is like addressing to, where it's contained, and that tells us something about the symbol, whether it's like initialized constant variable or uninitialized, or what other things were here, if it's mutable, yeah, things like this. So here's a typo, by the way. There's the I missing. And this one, yeah. So this helps us understand the static variables, or not non-static variables, and external and all this. So that's good. So we probably need to build this relationship. Well, this relationship is already there, but we need we need to collect the segments and the sections, I guess, or just the sections. I don't know. And then the other good information here is oh boy, this stuff here. So this information here, and this, it tells us something about the symbol, and this here tells us something about the symbol. So we're probably very much interested in this. Yeah. But this document also doesn't tell us how to work with vtable and RTTI and all this stuff. So it looks like this is something that we need to discover ourselves. I mean, ChatGPT already gave us some hints as to like, okay, how you can read that and this. But to me, it looks like it's not part of like any like framework or anything, or it's not a given. You have to do it yourself. Yeah. So maybe we just figure out everything our own, like how to actually interpret the symbols for higher level information, which probably will take a while to implement and get right. Yeah. But I think it should be possible. It's just a matter of time spent. Yeah. I mean, we had a look at a bunch of. What we can also still do is look at these tools here, O tool and NM. If there's anything interesting inside. Yeah. Okay. So this O tool and NM, let me see. O tool source code. Source code LLVM O tool. Open source Apple. Let me see. Page looking for can't be found. Oof. O tool. Object dump. We already looked at that guy. We looked at read object. We didn't look at object dump. LLVM object dump. We looked at LLVM NM, which gave us a list of things. Yeah. Okay, so I guess what we can do is we can look at LLVM LLVM 19.1 bin, and there is a LLVM object dump. Let's open a command prompt. Let's put this here. LLVM minus object dump dot exe minus help. It's not recognized. Okay, we made a mistake here. There we go. There we go. Okay. Oof. Disassemble. Huh. Disassemble symbols. List of symbols to disassemble. Disassemble all sections found in the input files. Okay. Okay, what does that do? Let's go to here. Let's do cdd that. Let's do object files. Oh. Well, let's see what happens if we just give it a we just give it the ZH file. Let's see what it says. It says nothing. Let's see, maybe we have to give it some arguments. Let's try all headers. Minus all minus headers. What does that give? Oh, okay, it can read it. Okay. Oh boy, stop it. Okay. Okay, there's super many options here. Super many options. Yeah. Okay, how about we test this next session? LLVM object dump, and we just go through all the options here and see what we can get out of it. Yeah, this looks like an interesting endeavor. We already previously we tested LLVM read object and NM tools, but we didn't look at this object dump thingy because ChatGPT wasn't mentioning it. So let's do that next session. Let's see what's in here. Weak binding info. Okay, universal headers. Yeah. No symbolic operands. Print indirect symbol table. Okay, I like it. It gives us some lists of, yeah, it can print us a bunch of lists of things. Okay. Symbolize operands. Symbolize instruction operands. Symbolize operands. Display source interleaved with the disassembly. Show all symbols. Disassemble. Disassembles all executable sections found in the input files. Okay, I wonder what this will do then. Disassembler color. What? Color output? Disassemble symbols. List of symbols. Disassemble all. Huh? Demangle symbol names. Okay, then yeah, let's the next session we test this guy here, see what it gives. Good. Okay, anything else we do this session? I don't think so. That should be it. Good. Then I hope you enjoyed. I wish you a great day or night. Until next time. Goodbye.